Intro to functions. A relation is a set of ordered pairs. A function is a special kind of relation. A function is a set of ordered pairs where each x corresponds to exactly one y value. That's something you want to make note of. Every x corresponds to exactly one y value. The domain of a set is x values, and then the range of a set is all of the y values. Let's look at an example. Determine whether or not the sets are functions, and then find the domain and range for each set. So we have to ask ourselves, is it a function? For every x, do you have exactly one y value? And looking at this first set, notice that 5 occurs twice in this set. 5 corresponds to 0 and 5 corresponds to -1. So this one is not a function because, again, the definition of a function is for every x you have one y value. And in this case, 5 corresponds to more than one y value, so it's not a function. We can still determine domain and range though. Domain is the set of x values, in this case -1, 5, 6. We don't need to rewrite the 5, it's already there. And then the range is the set of y values. So the range 4, 0, -3, and -1. That's your range. In the second example, we're looking to see if it's a function again. The definition of function is for every x you have exactly one y value. So notice here -1 only corresponds to 4, 5 only corresponds to 0, 6 only corresponds to -3, and 4 only corresponds to -1. So this example is a function. And the domain, again, is the set of x's, -1, 5, 6, and 4. And then the range is the set of y values, 4, 0, -3, and -1. In the next example, we're essentially doing the same thing. We're just giving what we're going to call this a mapping. And we're asking the same thing. Is it a function? Notice chevron only corresponds to 209. Shell only corresponds to 216. Gulf only corresponds to 221. And Exxon only corresponds to 216. So every x gets mapped to exactly one y value. That means this is a function. You can think of this as your x's and your y's, or your domain and your range. Every gas station has exactly one price. Whereas in this example, notice 0.7 carats corresponds to one price, 0.71 carats corresponds to two different prices. So if we think of this as an x and a y value, this 0.71 is corresponding to more than one y value, which means it is not a function. Another way to consider a set of ordered pairs is an equation. Recall that an equation represents a collection of ordered paired solutions. Our goal here is to determine whether or not these equations are functions. So if you put in an x value, will you get more than one y value back? In this first example, pick any x value you can think of and plug it in and ask yourself, will you ever get more than one y value back? For example, if you plug in 0, 2 times 0 is 0 plus 1 is 1. If you plug in 0, you're only going to get 1. If you plug in 2 for x, you get 5 back. No matter what you plug in for x, you're only going to get a single y value back. That means this is a function. In example B, we have to do a little bit of work. We really want to isolate the y. Notice in example A, y was already by itself. In example B, we want to do a little bit of work to get y by itself first. So the first thing we need to do is subtract the x squared. And then we need to eliminate the square on the y. To do that, we square root both sides. And remember, when you take the square root of both sides, we have to do plus or minus. So we have plus or minus 4 minus x squared. Now that you have y isolated, you can ask that question again. No matter what you plug in for x, will you ever get more than one y value back? And in this case, you will. If you plug in 0, for example, you'll end up with the square root of 4, which is 2, but you have plus or minus on it. So no matter what you plug in, it looks like you're going to get a positive and a negative. So you're getting more than one y value for every x that you plug in. That means this one is not a function. And then example C, notice y is already by itself, so we just have to ask ourselves the question, if you plug in a value for x, will you ever get more than one y value in return? And it looks like you will not. If you plug in 0, you'll get the square root or negative square root of 2. If you plug in 1, you'll get negative square root of 5. You're not getting that plus or minus thing like we had earlier. It's just the negative. So this one is a function. Function notation. If an equation truly does represent a function, then we can use functional notation. To write an equation in functional notation, we're going to solve the equation for y and replace y with the value f of x. We call this f of x. In this example, we're going to write the equation 2x minus 3y equals 6 using functional notation. The first thing we want to do is isolate y. So we'll subtract 2x on both sides of the equation. And then divide by negative 3. Y is equal to 2/3. Y is equal to 2/3 x minus 2. Once we have y by itself, we can replace y with f of x. So f of x equals 2/3 x minus 2. And we have function notation. Now let's work with functions. Consider g of x equals negative x squared plus 2x minus 1. In this case, we're going to first evaluate g of negative 2. Whenever you see something like this, just take whatever is in parentheses and replace the x's with what is in parentheses. So here we have negative, replace x with negative 2 squared plus 2 times replace x with negative 2 minus 1. And then we'll simplify. We get negative 4 minus 1, and that is negative 1. In the next example, we have g of x plus 4. So everywhere you see an x in the original g function, we're going to replace it with what's in parentheses. In this case, x plus 4. Negative x plus 4 squared plus 2 times x plus 4 minus 1. And then we go through and simplify. Negative, here we have a binomial squared, so we'll square the first, double the product, square the last, distribute the 2, bring down the minus 1, distribute the negative sign, and then combine like terms. We get negative x squared minus 6x minus 9. And in this last example, we'll replace all of the x's in the original g with what's in parentheses, x plus h. So we have negative x plus h squared plus 2 times x plus h minus 1. And we go through and simplify. Square the first, double the product, square the last, distribute the 2, bring down the 1, distribute the negative sign, And then we need to see if there's anything we can combine. It looks like there are no like terms, so we are done. Now I know that looks like a mess. There is a point to this. We're going to be using this kind of notation later with the difference quotient, and it'll have a little more meaning later. Consider the function y equals 2x plus 1. First, write it in function notation. F of x equals 2x plus 1. Again, we're simply going to replace the y with f of x. And now graph it. So we have an equation in slope-intercept form. Our y-intercept is 1. Our slope is 2. So up 2, right 1. And we can repeat that pattern as much as we want. Play connect the dots. We have a graph. Find the value of f of negative 1. So if we're doing it by hand, f of negative 1, we're going to replace the x with negative 1. We get negative 2 plus 1, which is negative 1. Now that's just coincidental that what you plugged in is what the equation returned. What you really want to note is the graph. Where is this? Where is x negative 1? X is negative 1 here. Notice that when x is negative 1, the equation returns negative 1. So describe what that means. It means you're looking at a coordinate on the screen. So if I gave you an alternate point, for example, this one, that is the coordinate 1, 3. If you know that, we could also say that f evaluated at 1 is 3. When you plug in 1 for x, the equation or the function will return the y value of 3. Next, we'll look at domain of functions. There's going to be 3 different kinds of functions that we're going to focus on and their domain. First of all, polynomial functions. Those are easy. Domain of polynomials will always be all real numbers. Negative to positive infinity, all real numbers. With rational functions, remember rational functions are basically fractions. We've seen these before. And remember, you have issues when you have division by 0. So we want to watch out for division by 0. We've seen those restricted values already in the past. And with radical functions, we want to watch out for negative radicands. Remember, a radicand is what's under the square root. Essentially, you want non-negative radicands. You want the stuff under the radical to be positive or equal to 0. So non-negative means we're going to take whatever is on the inside and force it to be greater than or equal to 0. For example, let's find the domain in part A. Notice you have a radical here. So essentially, we want what's under the radical, the radicand, to be non-negative. So we're going to take whatever is under the radical, in this case x minus 4, and we're going to set it greater than or equal to 0. We don't want it to be negative, so we have to make it positive or equal to 0. And then solve this. Add 4 to both sides, and we get x is greater than or equal to 4. That's our domain. So our domain is 4 to infinity. We can be equal to 4 and anything bigger than 4. In example B, notice it's a polynomial. We don't have any division. We don't have any radicals. This is a polynomial. The domain here, all real numbers. No work. We automatically know that it's a polynomial, so no issues with domain, all real numbers. With C, we have a rational function. So we need to figure out what causes the denominator to equal 0. We've seen this already. We've seen this in the past. So let's take our denominator and force it to be 0. That way we'll know what values of x cause division by 0. Here we'll factor. Set each factor equal to 0. And then solve. X equals -2 and x equals -3. Both of those are restrictions. We remember seeing that in the past. That's what we do not want in our domain. So the domain is everything except for these. So if you want to make a note, we can say x is not -2 and x is not -3. The way we write our domain in interval notation, -infinity up to -2 with a union, -2 to -3, union -3 to infinity. So notice we're including everything except for -2. We skip -2 and we also skip -3. Everything else is part of your domain. In this example, we have two things happening. We have a radical, but we also have division by 0. So we'll start with the radical. Notice the radicand is x minus 4. So in the past, we set it greater than or equal to 0. Right? Remember, when you have a radical, you're going to take what's under the radical, the radicand, and force it to be greater than or equal to 0. But in this case, because it's in the denominator, we want to make it strictly greater than 0. We don't want to have equality, because if you have equality, you're dividing by 0 in this case. So when it's in the denominator, make it strictly greater than 0 and solve. X is greater than 4, so our domain, 4 to infinity. Next, we'll look at combinations of functions. Let f and g be some functions. Then we can combine these functions to create new functions in the following ways. So this is just saying that we can add functions. If we have f plus g, we can just add those separately. If we have f minus g, we can subtract those functions, and so on. Operations are okay with functions. Add, multiply, subtract, divide, we can do that. For example, if f is the square root of x and g is x minus 5, find each of the following. F plus g of x. We can rewrite that as f of x plus g of x. And then f is the square root of x, g is x minus 5. There's nothing to combine there. Those are not any like terms. So we have it. This is f plus g of x. F plus g of 4, well, we already know what f plus g is. Now we want to do f plus g of 4. So to do this, we're going to simply replace all of the x's with 4. So we have the square root of 4 plus 4 minus 5. That is 2 plus 4 minus 5, which is 1. F plus g of 2. Again, we already know what f plus g is, so all we're going to do is take this equation, and every time you see an x, we're going to replace it with -2. So we have the square root of -2 minus 2 minus 5. That is the square root of 2i minus 7. Then we'll just put that in standard form. -7 plus the square root of 2i. And that is f plus g of -2. Next, we'll talk about the domains of combinations of functions. The domain of f plus g is the same thing as the domain of what you end up with. Like up here, we would just look at the restrictions on this example. So no extra rules. You're just using the same domain restrictions and domain rules that you used earlier. For example, let's look at f plus g and its domain. So earlier we already found that f plus g of x is the square root of x plus x minus 5. Now we need to look at its domain. Remember, you're looking for polynomial, rational, or radical. In this case, we have a square root, so we have a radical here. We want to take whatever's on the inside and force it to be non-negative, greater than or equal to 0. There are no other restrictions, so the domain is 0 to infinity. For f times g, first we need to find f times g. F times g is the square root of x times x minus 5. We'll distribute and get x square root x minus 5 square root x. Now look at the restrictions. We have a radical again. X is under the radical, so we're going to make that greater than or equal to 0. And we have the same domain, 0 to infinity. And then with f divided by g, f square root of x divided by g, which is x minus 5, we have an extra restriction here. Notice that the square root of x still happens. So we still know that x has to be greater than or equal to 0. That's still part of the restriction. But we also have this denominator, x minus 5. And remember, with x minus 5 in the denominator, we need to set it equal to 0 and figure out what that is. In this case, 5. So we have to exclude 5. So we have an extra restriction here. Still, the domain has to be greater than 0 or equal to 0, but we have to exclude the 5. So the domain starts at 0 and goes up to 5. We have to exclude the 5, and then we continue on forever. So the domain starts at 0 and goes on forever, but we skip 5. 5 causes division by 0, therefore it's not part of the domain. In this example, we'll find some more operations on functions and their domain. So first we have f minus g, 1 over x minus the square root of 4 minus x. In this case, we have two issues. We have division by 0, so we know x cannot be 0. And we also have this radicand, 4 minus x has to be greater than or equal to 0. Whatever's under the square root, force it to be greater than or equal to 0. So let's solve this. Subtract the 4, then divide by a negative 1. Remember, when we divide by a negative, that flips the symbol. So we have two things we need to take care of. Can't be equal to 0, and it has to be less than 4. So our domain, this time we're starting at negative infinity, and we're going to 0. We're going to exclude the 0 and continue to 4. And then in the next set, we have f divided by g. F divided by g. So again, we have two issues. We have division by 0 here. X cannot be 0. And we also have this radicand. 4 minus x has to be greater than or equal to 0. But in this case, it's in the denominator, so we can't have equality. So we're going to make it strictly greater than. Again, when it's in the denominator, we don't want to have the equality part. Continue solving. Negative x is greater than negative 4, and x is less than positive 4. So essentially, it's the same thing as what we had earlier. We have can't be 0, and x has to be less than 4. The only difference is we can't include the 4. So our 4 will have a parenthesis rather than the bracket from earlier. Next, we have the difference quotient. This is basically intro to Calc 1. Those of you who are heading to Calculus 1, you'll get very comfortable with the difference quotient. Here we're just looking at the function notation part of it. It looks a little intense the first time you see it, but it's really not that bad if you just treat it like it's function notation. So we're going to find the difference quotient for the following functions. 3x minus 4. I recommend you write the difference quotient every single time. It'll help you learn it. So before we do our example, let's rewrite the difference quotient off to the side. Then we're just going to take it one piece at a time. F of x plus h. Keep in mind that's just function notation. All you're going to do is every time you see an x in the original f, you're going to replace that x with what's in parentheses. In this case, x plus h. So we have 3, replace the x with x plus h minus 4. And then we're going to subtract f. So we're going to subtract the original f, which is 3x minus 4. Make sure you put it in parentheses because we want to subtract the entire piece. A very common mistake I see is students will forget to put it in parentheses and therefore forget to distribute that negative sign later. So be careful with that. And then all of that is over h. So we're just going to put an h in the denominator. And from here, we'll go through and simplify. 3x plus 3h minus 4 minus 3h plus 4 all over h. Now go through and see if anything cancels. Notice that 3x and negative 3x cancel. Negative 4 and 4 cancel. And then we are left with 3h over h, which is simply 3. So the difference quotient for 3x minus 4 is 3. In our next example, we're looking at x squared plus 2x plus 1. Again, let's start with the difference quotient. But this time let's use g. G of x plus h minus g of x all over h. Write down that generic formula every single time and it'll help you learn the process. First, we want to do g of x plus h. Again, think of it as function notation. All you're going to do is you're going to write g, but every time you see an x, replace it with what's in parentheses, x plus h. So we have x plus h squared plus 2 times x plus h plus 1. Then we need to subtract g of x. So we're going to subtract in parentheses, just copy the original problem. Make sure you put it in parentheses so we remember to distribute the negative sign. All of that is over h. And at this point, we'll just go through and simplify. X plus h squared, we need to square the first, double the product, square the last. Then we distribute the 2. Bring down the 1, distribute the negative sign. All of that is over h. And now go through and see if anything cancels. X squared cancels with negative x squared. 1 and negative 1 cancel. And 2x and negative 2x cancel. So at this point, we have 2xh plus h squared plus 2h all over h. Notice the numerator has an h in every single term, so we can go through and factor out an h in the numerator. So when we pull that h out, we have 2x plus h plus 2 all over h. And now the h in the top and the bottom cancel, so we're left with 2x plus h plus 2. And that is the difference quotient for this example. Now right now that doesn't mean a whole lot. You'll see a lot more detail in Calc 1, those of you who are heading to calculus. For now, we're just dealing with, can you get to this point? We're not going to talk a whole lot about what you do with this. We don't have the tools yet to talk about how to use this in calculus.